In our early analysis, we looked at how the current phasor responds to changing voltage magnitudes. It's important to note that this analysis is quasi-static. We aren't accounting for the transient or dynamic characteristics of the network yet. The goal is simply to build intuition around use of phasors in circuit analysis. Let's attempt to conduct a couple more simplistic investigations onto the same circuit, the first being understanding how the power is flowing in the given circuit. Let's revisit the circuit to understand what is being discussed. It consists of two nodes with respective node voltages E1 and E2, and the intent is to calculate the power flow. To answer this, we need to calculate the apparent power, S, which can contain both real and reactive power components. Typical formula for calculating apparent power is shown here. This deceptively simple formula is usually a source of confusion if we do not align it with the assumptions of the circuit. First, let's understand how we would apply this formula. We are calculating apparent power S leaving a particular node. Therefore, it will be a multiplication of voltage at the node terminals and the complex conjugate of the current leaving the node. The leaving bit needs to be interpreted correctly for aligning our math with our assumed parameter directions. Recall that we have assumed direction of current is from terminal 1 to terminal 2. Therefore, at terminal 1, the apparent power is multiplication of terminal voltage E1 with conjugate of current phasor I, which, as per our assumption, is leaving terminal 1 and going towards terminal 2. However, for same calculation at terminal 2, we must use minus I. This is because, if I is the current entering terminal 2, then minus I is the current leaving the terminal. Accordingly, see the use in formula. After some algebraic manipulations, we arrive at expressions for S1 and S2. Now we calculate sum of S1 and S2. This will give us the total apparent power, leaving both the terminals of the circuit. Conservation of energy indicates that this should be equal to total power consumed by the connecting tie line. Let's see if the mathematics agrees with our logic. After carefully managing the complex terms, we arrive at an expression for total apparent power to be magnitude of E1 squared plus magnitude of E2 squared minus twice the real part of E1 times the conjugate of E2, all divided by conjugate of the impedance Z. A bit deeper mathematical investigation will reveal that the numerator is always real and always non-negative. We encourage the students to prove this is true for mathematical rigor. With a bit more reorganization of this expression, we can land at the conclusion that the apparent power draw from the nodes will only depend on nature of the branch impedance, that is, by the extent that it contains the resistive and reactive components. This agrees with our intuition that power flow for this circuit should be driven by the line impedance. It goes without saying that underlying simplification for this analysis is that the terminals 1 and 2 are assumed to be infinite bus, which means that they are infinite source of active power, infinite source or sink of reactive power, and capability to infinitely regulate their voltages to any value. In reality, the practical sources are limited in both capacity and therefore regulation. Therefore, the circuit designer or the power system engineer have to design the network in the manner such that these limitations are not breached under normal operating conditions. While we've just analyzed the total power generated by the two sources, it is important to understand the factors affecting the individual contribution of each node. Revisiting the equation for power at a given node, we see it is expressed as a function of the voltages at both the generating and receiving ends. Utilizing Clifford product formula for vectors, we can rewrite E1 times conjugate of E2 as Cartesian combination of their dot product and cross products. This will allow us to reorganize the expression as shown. By substituting the expression for admittance with its respective conductance G and susceptance B, we can delineate the active and reactive power components as shown here. Although the calculation has been done for node 1, it's recommended that similar exercise is done by the student to derive the expressions for node 2. A key observation here is the element of power exchange. A closer look at the expression, we note that there is a specific component of active power generated, which is governed by the phase lag between the sending and receiving node voltages. A keen observer would note that this component has nothing to do with lossy characteristics of the tie line, and deriving expressions for the receiving node, it will be found to be completely balanced. This phenomenon is significant because it dictates the behavior of parallel voltage sources, particularly synchronous generators. This is a vital connection for those interested in the concepts of synchronization and hunting in rotating machines. At the same time, we can see that there is a term available in the expression for active power that accounts for power consumption related to lossy component of tie line, and if added to the expression for power generated at the receiving end, will result in total active power consumed by the lossy line, thus ensuring conservation of energy. Interested students can consider exploring the underlying rationale for the expression of reactive power generation as well. Let's walk through this animation to visualize the power contribution behavior at the nodes we just discussed. Here is a well-known circuit, two voltage sources at nodes 1 and 2 connected via a tie line with finite impedance. Also shown is the associated phasor diagram depicting node voltages E1 and E2 and tie line current I. Unlike previous circuit calculations, for this illustration, the tie line impedance is a composite of resistive and reactive components, that is, 5 ohms each. This will allow us to see the influence of the conductance G and the susceptance B as were worked out in the nodal power equations. In the phasor diagram, reference phasor E1 has been held constant, whereas the phasor E2 has been held at a leading angle of 30 degrees. As we vary the magnitude of E2, the bar graphs on the right dynamically track the active and reactive power generated at each node, calculated using the formula shown below. In the power bar graphs, note that the power at each node is dissected into two terms, the line component and the exchange component. This mapping helps illustrate how these individual terms vary as the node voltages change. We also show a purple bar at the far right of the graphs that represents the actual power demand of the tie line. This serves as validation. The sum of the power generated by both sources must match this total line demand. We observe that power exchange terms at either node follow a largely consistent trend, irrespective of the magnitudes. That is, the node with the leading voltage phasor, in our case node 2, will be the generator, whereas the node with the lagging voltage phasor will be the receiver of the power exchange term. In contrast, nodal contribution to line losses varies with the magnitude of node voltage phasors. See the expression. The phasor voltage with the larger magnitude is likely to be the major contributor to the tie line power demand. This is because it is more likely to have vector difference of the node voltages, that is delta E, aligned with it. Consequently, the associated dot product, as per the expression, will yield a high correlation. Students would note, however, that the nodal contribution can, for some voltage difference, be negative as well, which basically means that the generating node is contributing power not only towards the tie line's lossy component, but also to the transfer of power to the other node. However, when summed, the nodal contributions equal the active and reactive power demand of the line, as shown by the purple bar. On the other hand, the power exchange terms at the nodes always cancel each other out for any combination of node voltages. Finally, this time let's see how power contributions vary when we vary the phase gap of the node voltage phasors rather than the magnitudes. In this case, we are keeping the magnitude of the voltage phasor E2 to be constant, however, we are changing the phase gap with respect to reference phasor E1. Once again, the intention is to analyze the variation in power contribution as seen in the bar graphs. As far as power exchange terms are concerned, the rationale is pretty easy. The node having the leading voltage phasor will be the generator, whereas the node having lagging voltage phasor will be the receiver. On the other hand, the power contribution to the tie line is noticeably seen as equally shared by the two nodes. We encourage students to verify this via equation analysis as well. It goes without saying that the condition when both the voltage phasors are fully aligned with each other and are of same magnitude is ideal condition for the system. This means that there is no undue wastage in servicing the line losses, especially when there is no load demand or having power exchange from one generator node to another. The generators can in this state be deemed to be fully synchronized. To conclude, let's quickly summarize the key concepts we've covered in this discussion. We began with a fundamental circuit, two ideal voltage sources, modeled as infinite buses, connected by a tie line with a specified impedance. Our primary goal was to analyze how the circuit current responds to variations in the magnitude and phase of the bus voltage, E2. While a quick calculation provides the current for any single state, we took an analytical route to investigate the trajectory of the current's phase angle as magnitude of node voltage E2 changes. By establishing the reasoning behind these phasor transitions, we identified the specific domain limits where the current shifts between quadrants. Eventually, the student was also encouraged to determine at what point it should be conceded that the current has reversed its direction. From there, we transitioned into power flow analysis. We spent a couple of minutes addressing the common pitfalls of the complex power formula, specifically, the importance of consistently mapping the assumed current direction to the apparent power expression. Subsequently, we analyzed the total power generated. We reached the logical conclusion that the total generation must align with the total consumption, which is dictated entirely by the characteristics of the tie line. Finally, we moved to the most nuanced part of our discussion, determining the individual contribution of each node to the total power demand. We demonstrated that these nodal contributions are intricately linked to both the voltage magnitude difference and the phase gap. In this section, the concept of power exchange between nodes was illustrated and saw how full synchronization of node voltages can result in a dramatic reduction in wasteful power exchanges and line losses. The intent of this monologue was to very briefly introduce students on foundational framework of power system analysis via a problem-solving approach. Moving ahead, we will explore more problems that require phasor-based circuit analysis techniques and how they can be used to interpret the behavior of commonly deployed three-phase circuits in power distribution networks. Eventually, more intricate tools such as symmetrical components, bus admittance, and node impedance matrices and numerical methods of power system analysis will be discussed.